Hello everyone. Today we will be looking at an aircraft wing model. This wing simulates the assembly of the wing to the fuselage and predict what factors may affect the engine, ground clearance and wingtip displacement. So here you can see few examples of very low ground clearance, and you can see here that the engine bottom of the engine is made flat instead of round, just to get an extra bit of ground clearance. This you can see this is how the V5 version of CATIA V5 version of 3DCS software looks like. At the end of this PowerPoint, I will be showing a small demo video of how the model and the software looks like. So you can see this model was not built with actual data, and few realistic assumptions were made, like material properties of the wing, assembly sequence, all the tolerances used, weight of the engine, and few others. So if you see 2 points here, these are the measurement points. These will represent the ground clearance measurement, and this point at the end of the tip will represent the wingtip displacement. So now we will be looking at few of the factors that may have an effect on the ground clearance and wingtip displacement. So first factor that may have an effect on the wingtip displacement is the effect of gravity. So here you can see the measurement numbers of around 30 mm and 6 mm on the wingtip and the ground clearance. So this tells us that wing displaces around 30 mm due to the weight of wing and the engine. In the picture here, you can see a color contour of the displacement on the wing. So within 3DCS, at any moment on the assembly sequence, you can export a displacement file and see a color map per part. So this shows the color map of the displacement on the wing. So the second factor we thought that could affect the measurements is the position of engine. So here you can see our engine was first at nominal position, and then we tried 3 different positions of the engine and measured its effect on the tip displacement and ground clearance. So these are the 3 positions: min, nominal and max. So if you see the measurement numbers, you can see at min position the tip displacement measurement reduced by just 0.3 mm, and at max position the tip displacement increased by 0.36 mm. So we can say that the position of the engine doesn't really matter and doesn't really affect the measurements at the tip displacement. You see these big numbers for the ground clearance at min and max position, but that's just because of the shape of the wing. As we move along the wing, because the reference point for the ground is just constant, the ground clearance increases or decreases. Just to give a point that the engine movement of engine doesn't really affect the tip displacement, or the ground clearance. So till now we were just looking at the results with perfect parts, which means there were no tolerances included, and the results were just the nominal build results. There were no simulations ran, and no variation was included. So the third effect we include is we include tolerances, or we include imperfection in the parts. So all these parts all these points you see are the tolerance points, and we all these points have a linear independent surface tolerance of 5 mm, and again that number was just another assumption. So now that we know that the position of engine doesn't have any effect on the measurements, so we went back to nominal position of the engine and ran our results with tolerances. So these results include the effect of gravity as well as the tolerances. So you can see there's a big difference between the nominal numbers and the variation numbers. One thing important to note is these numbers are the value of ranges, and these are just the nominal values. The picture here is from the actual DCS results and gives us all kind of values like min value, max values, nominal values, and it tells us how many runs were run. So we ran 2000 samples, estimated low, estimated high, and estimated range. We are looking at the values of estimated ranges. Another good information that this simulation result gives us is that it lists all the contributors affecting the measurements. So from the list you can find out the top contributors affecting the measurement, and you can start working on them and looking into them. So from the list we can see the first 7 contributors is the same tolerance, and it affects about 99% of the variation. That tolerance is the black box tolerance on the fuselage, which was 5 mm. So what we did is, now that we know that the main contributor is the fuselage tolerance, which is 5 mm, we did another study or another tolerance scenario with a lower tolerance of 3 mm. So once you find out the main contributor, you can start working on it. If it's a tolerance, you can look into how to reduce the tolerance by either including a fixture or improving the design or improving the quality of the parts. So just to make the model simple, we ran another set of results with a tolerance of 3 mm instead of 5 mm. So here are the results. Another thing about 5 mm results is that you set your spec limits, and if the results are outside your spec limits, you will see the red color here. So with 3 mm tolerances, we ran another set of results, and one thing you can notice is now everything is green, and if we look at the numbers, we get about 40% less variation than we were getting at 5. And again it lists you all the main contributors and gives us their contribution. So that's it for the PowerPoint presentation. Now I will just run a quick video and demo the model and the software. This is how the CATIA V5 version of 3DCS software looks like. Here you can see there's a CATIA tree and there's a DCS storage which contains the DCS tree. It has 4 parts: wing, reference, engine, and fuselage. And if I expand the DCS tree, it has all those parts. It has moves and measurements, and tolerances are included within the parts. This is the wing. This is the reference part for the ground. We have engine and we have fuselage. Just to make the model simple, we just created wing as one part instead of assembly. So this shows all the points which were used for DCS model. These include all the tolerance points, measurement points, and move points. If I do a nominal build, that builds the assembly in running all the moves. Yeah, this is the separated position. So if I go through some of the moves which were used, the first one was a rigid body move. First one was the rigid body move. That's just putting the wing to the fuselage using a rigid body. And the second one is input FEA data. That move is used to input the mesh and stiffness files we create using DCS StiffGen. And after we import the mesh and stiffness files, now these parts are compliant. So we need to import a mesh and stiffness file for all the points we want to be compliant. So the next move is a clamp move, which is we are clamping the wing to the fuselage using all these points. If you open that move, it will list all the object points and the target points. You can see all the object points are in wing and target are in fuselage. And we have all bunch of options for different type of clamps. The next move is apply gravity. So we can select a part on which we want to apply gravity. So after the wing is clamped to the fuselage, now we apply gravity and the wing will deform according to its weight. So rest of the moves is we just apply forces on the wing according to the weight of the engine. We apply that at nominal position, min and max position. So these are the measurements which were used. You can see a tip displacement and ground clearance. Measurements were used, just a couple of them. All of them were point based. If I open that, it says the point on the engine. If I open that, it says the point on the engine, and the target point, it says from to. So from is on the engine and to is on the ground. So if I do it again, now you can see it's a point measurement from engine to the ground. That gives us the value for the ground clearance. And now we have tolerances. We have linear tolerances, and the value is 5 mm. Value was assumed to be 5 mm. And in fuselage we have two tolerances for two different scenarios. Another thing you can do is just waiting. So another thing you can do is you can turn on and off the moves and see min and max position of the engines. So if I do nominal build and turn on the min position, it will move to the min. If I do max, then it will move to the max. So the last thing I want to show is when I do similarly, I can turn on and off the tolerances, and it results will run depending on which tolerances are on. So we will go back to the nominal position, and the last thing I want to show is at nominal build, if I hit deviate, we will see the wing moving according to the effect of gravity as well as according to the effect of all the tolerances used. So you can see the wing, it's actually deforming. You getting?